Okay, this is a video walkthrough on how to calculate all the lengths and volume for a concrete stair. This is a level 3 carpentry problem. Comes up in G line, G6 if you're following along with your modules. So we have all the lengths here, but the question is, how did we get to that? And this is on the left side, we have what we're given. So I'm going to take you step by step through how to calculate all of these, and then we're going to go through how to calculate the volumes. But you can't get the volumes until you've gotten many of these measurements. So let's run through what that looks like. So your first step whenever you're doing these is to figure out your unit rise and your unit run, or what I'll call it is just the rise and the run for each step. Here's the process here. This is a simple procedure. This comes from first year, second year, all the way through. This should be second nature to you at this point. Total rise divided by desired rise gives you 19.2 rises. Can't have a fraction of a rise, so we're going to round that down to 19. So 19 will be our number of risers. Once we've found our number of risers, we're going to put that number back into the total rise to figure out our true rise per step. And we get 192 in this situation. The run was given to us here. So now we know we have a rise of 192 and a run of 310. This is all in millimeters. I haven't written in the symbol for millimeters, but that's what all of these numbers will be, and we'll switch that over once we get to the volumes. So with these two numbers, you should use Pythagoras to figure out the unit of bridge per step. We'll need that moving forward. And we can also call this our key triangle for solving all the other lengths that are triangle related in this problem. A squared plus b squared equals c squared. Again, something you should be familiar with and be able to do second nature at this point. So here's our key triangle, and you'll see this come up now as we move forward. So now we're going to roll through all the different requests for us to solve. So the first one was the rise, which we figured out. B was the run, which we were given. C was the unit of bridge, which I just showed you. D ends up being the soffit thickness. Let's have a quick look. There's D right there. And then D makes a little triangle here. They ask us to solve for E as well. We need E so we can determine what's going on in this section here. Okay, so here I've drawn that triangle as it appears on the handout. What I suggest you do at this point is flip that triangle around so you can see it in the same orientation or similar, just flipped orientation that we had, that key triangle and the rise run triangle. And it can be a little bit confusing if you try to determine that just based on this orientation. I think it's helpful to get them all in the same direction. You can see here I had E erased here because I had to sort of think twice about what side these were on once I flipped it. Okay, so once it's all flipped, we realize that E is on the hypotenuse and D is down here on the adjacent. And then all we're going to do is ratio and proportion that off with our key triangle to figure out what E is. And that's what I've done here. Cross multiply 150, 364.6, divide by 310, and E comes out to be 176.4. I also suggest when you're doing this math to keep all your answers to one decimal while we're in millimeters. And you'll see that throughout this problem. Moving forward, we have F, which is the same as E. Again, we'll show you. There's your F. It's just the same situation up on the higher step. We move it up here so we can see what we're doing because we need to solve for G. Here's G. And I've got it written out as the rise minus the landing thickness plus F. And then I'll just show you exactly how that looks here. So this dimension here, G, we can figure out by taking our rise, this is our total rise, subtracting our landing thickness, and then adding F. And that should leave us with this. Now in this situation here, the way that this drawing is showing us is not accurate to the numbers. Our drawing is showing us that the landing is thicker or longer, I guess you could say, than the rise. It's not always the case, but we just stick to this formula and you'll get an answer for G. We get 168.4. And then our next problem to solve is H. And again, we have a triangle with G in the opposite dimension and H along the adjacent dimension. And we're going to flip that and ratio it off against our rise-run triangle. Here I've done that. There's your G, there's your H. Flip it around, put this one next to it, write all the dimensions in here. Now you can see that H is proportional to 310 and G is proportional to 192. So G being 168.4. So here we have it there. Cross multiply these two, divide, and H is 271.9. Alright, moving on to K. And you can see K is just a formula, landing length minus H minus nosing. Let me show you what that looks like up here. K being this dimension here. So our landing length taken from the back here to the tip of the nose. We have to subtract that nose and we have to subtract H. And that'll give us K. And that's what we're doing down here. And we get 798.1 in this situation. Next thing we're going to try and solve for is M. M is fairly straightforward. It's our total rise minus our landing thickness. Let's take a look at that. Our total rise right to the top here minus our landing thickness will give us M. And after M we'll try to solve for L. And you can see here that we have a very big triangle, M and L involved with that. So here we have M calculated to 3,448 millimeters. Now L, here's the triangle I just showed you, drawn out. The orientation is fine, no need to flip or anything like that. Proportion it off against our rise-run triangle. Everything a function of the rise-run triangle in this math. L is the unknown, M we calculated for, so we put that in here. Proportioned off against the hypotenuse of the rise-run triangle and the opposite arm, or the rise, being 192. Cross multiply, divide, L becomes 6,547.6 millimeters. And our little bonus dimension, which you won't find on here, will be, let's get rid of that, will be this, which we're calling P. This distance here, or you can take this distance from the heel to the short side of the nose if you didn't have the nose on there. And what that is the cross section of the step, and it gives us the total width required for the stringer to the theory line before we add the nosings. We call that P. So if this is our P triangle, we have B, which is going to be the hypotenuse of that triangle. P will be in relation to the rise on that step. Here it is flipped around. You get P. There's the run. I hope you can visualize this a little bit more abstract. You can see how I had that in the wrong place. I just crossed it out just to show you. That's easy to make that mistake. So make sure you have these in the right spot. And here's your triangle to proportion it off against. So P is proportional to 192. And the run, which we know is 310, is proportional to 364.6 in this situation. Cross multiply, divide, P 163.2. And that does it for our dimensions. We've got all of those figured out now. And our final move is to calculate the volume for this set of stairs. So we have a couple things in here that will help us with the volume. We have our landing thickness. Our landing length, 1100 mil from here to here. We have a landing thickness of 200 mil. a stair soffit thickness, which is this dimension here, of 150 mil. We also calculated our length of soffit with L. We're going to use that, and that's why we take it all the way down to there, so we can figure out the length of the soffit. And we have our stair width. So if this were spun around and we were looking straight on these stairs, we would see that our stairs are 3,250 millimeters. So now is the time to shift this all over into meters, and that's just done by moving that decimal point 3 spaces. Here's our volume calculations. So the concrete volume of this entire set of stairs is 3 different volumes added up. The volume of the soffit, the volume of the treads, then the volume of the landing. Here's what I mentioned here. Change everything to millimeter. If you don't, you're going to get your answers in the millions, and you're going to have to divide that by cubed 3 times. So it becomes a bit of a task. So again, I recommend doing that now before you get into multiplying these together. We have, for the volume of the soffit, we have L, which we figured out. We have the soffit thickness, which I just showed, and we have the stair width. Multiply those together, we get 3.192. And then I'll just show you again. That is a rectangle, basically, as my cursor follows through here. That is that rectangle there. The next thing we're going to figure out is the volume of each step as it relates to this triangle here. And what we need is the area of each of these triangles, that being a function of the rise, and this section here being the run and the nosing, to get the area of this. It's basically like calculate the area of a triangle. So we'll get that, and then we'll multiply it by the stair width, and we'll multiply that by the number of treads involved here. Okay, there's a discrepancy here between the module and what we do on our math sheets. Module will have you taking this step as well as part of the tread calculation. We don't do that because we will calculate the entire landing up to here, whereas the module will take the landing to K. Okay, and it's a bit of a wash. There's a bit of an overlap here, and there'll be a slight discrepancy if you do your math the way the module suggests you do it. But just recognize that really, if you're ordering concrete, there's no, it's not enough of a difference to matter. So we like to do it this way, and we think this way is more accurate. And here I've walked you through what that looks like. Number of treads, area of treads, and then stair width. Number of treads is 18, always one less than the number of rises. Here's our area calculation. So that would be our tread depth, which is the run plus the nosing, times the rise, divide by 2. There's your area of triangle. And then multiply that by the width of the stairs, 3.25 meters. And a final calculation, very straightforward. The volume of the landing will be the length of the landing times the landing thickness multiplied by the width of the whole set of stairs. And we get this number here. You can put these 3 together if you like and give yourself a total volume. But that's the gist of calculating volume and dimensions on a stair. So we go through all these steps for calculating all these lengths with triangles to make our volume calculations easier to visualize and to make it possible, because we need some of these dimensions to figure that out. So I hope this video helps you walk through how to calculate the math for these concrete stair calculations.